Hello and welcome to the wonderful world of mathematics. Today we're doing 4.7 inverse trigonometric functions. We talked a lot about sine, cosine, tangent, cotangent, secant, and cosecant. However, now in the last section of this chapter, we got to turn it all on its head. Inverses. Inverses of all of these functions. Let's start it out. What are we going to be doing? Evaluating and graphing inverse sine functions. Evaluating and graphing other inverse trigonometric functions. Evaluating compositions of trigonometric functions. Alright, so we got a pretty substantial amount of stuff to do. I say we just go for it. I mean, if you'd like, I guess you have the option of pressing pause, taking a nap, if the first 20 seconds have tired you out enough.
Boring.
But I'm going to keep going.
Mr. Valeni, teaching advice, make it not boring.
Think back, Algebra 2, Algebra 1, what do we need to have an inverse of a function? We need to be able to pass the horizontal line test. Horizontal line test means I'm going to sit here and I'm going to keep drawing horizontal lines, well, as close to horizontal lines as I could possibly make, through this entire function. If my horizontal lines hit, just erase so we can see one of them. If my horizontal lines hit at more than one spot, which with a periodic function, a function that's going to continuously repeat, obviously that's going to happen, and it's going to happen way more than one time. It's going to happen infinitely many times. So, what do we do about that? In order to have an inverse for the sine function, for the cosine function, and so on, we need to restrict the domain. We need to restrict how far it moves on the x-axis. And that's what this is right here. The highlighted in black part is where we are going to restrict the domain. Why have we chosen to restrict it there? Because it doesn't repeat any of its values between here and here. If I restricted it between here and here, vertical line test tells me that's still not good enough. So that's why it's restricted specifically from negative pi over 2 to pi over 2. That makes the function 1 to 1, meaning there's one output for every one input, and that it can pass the horizontal line test, which is just another kind of fancy way of doing that. So by doing this, I have an interval, negative pi over 2 to pi over 2, which takes on the full range of all of the sine values. Okay, it's not like we're cutting out any information here. We're taking all of the same sine values, all the values that would happen, but we're not choosing all of the ones that continuously repeat and repeat and repeat and repeat. That's kind of just extraneous information that's not really super necessary. So we can kind of cut it out, make our inverse. We can see that the function is increasing on that interval. It's just interesting. And we've made it 1 to 1 because of this. Okay. Now, when I create the inverse sine function, I create a new function called the inverse sine. Now, this one mostly is titled inverse sine function. This is the exact same thing. These things are interchangeable functions. So this says arcsine of x. This says the inverse sine of x. But they both mean the exact same thing. It's just different notation for if you encounter one or the other. The important thing we want to remember with the inverse is that it is not the same thing as this. When we had something, the cosecant, secant functions, those are reciprocals, 1 over sine, 1 over cosine. That is not what we have created here. We have created the inverse sine, and those two things are not the same. That's a very common mistake, and I just wanted to clear that up for a second before going any farther. Alrighty, and then at the very bottom here, we basically have just a definition of what an inverse sine happens to be, which basically what it means is that the arcsine of x means that the angle or the arc whose sine is x. And I'm going to continuously repeat that as we go through examples to hopefully kind of engrave it. So let's look at some examples and let's just see how this works. Arcsine of negative 1/2. Now the first thing you might notice is that this number is no longer an angle value. Our solution is the angle value now. Before we were going and saying the sine of an angle and then that's the ratio. This time we're saying the arcsine of the ratio, what angle does that correspond to? Okay? Think about a unit circle. Where I have a sine of negative 1/2 is definitely in the bottom two quadrants, and it happens at two different places. One is over here, and one is over here. So now I kind of have a choice. Do I want it to be in this quadrant, or do I want it to be in this quadrant? Well, I know that the inverse function is restricted between negative pi over 2, which would be rotating down this way to here, as well as pi over 2. So my inverse is restricted to these two quadrants, the negative quadrant down here and the positive quadrant up here. So I don't want to look at this one. Okay, I just want to focus on this one. How could I define this particular angle? Well, some of you might immediately think, I know if I look at my unit circle that I'm going all the way around and it looks like it's going to be 11 pi over 6. Is that correct? Well, unfortunately, no, it is not. Because 11 pi over 6 does not fall within this restriction, negative pi over 2 to pi over 2. Okay, I need something that is either less negative than pi over 2 or a little more positive and up to pi over 2. So what's another way of expressing this angle? Perhaps maybe using a negative angle. 11 pi over 6 is the same thing as negative pi over 6. Alrighty, so that is my solution for part A, negative pi over 6. So it takes a little bit of, a little bit of a complex thought process, but after you do it a couple times, it will become easier. Now let's look at part B. This time we're not using arcsine, we're using inverse sine. Not a big deal, doesn't really matter, it just changes how you say it. This one was arcsine of negative 1/2, this one's inverse sine of square root of 3 over 2. So now let's look again at a unit circle. And where does the sine equal square root of 3 over 2? Okay, that's going to be in two different places. It's positive, so it's in the top two quadrants, there and there. Now again, I have the same restrictions. It's going to be something on this half of the unit circle, so I don't really care about this one. And a way that I can express this would be pi over 3 if I'm looking, or if I just happen to know that value. So an angle whose sine is square root of 3 over 2 is pi over 3. Is pi over 3 within the restricted domain? Yes, in this case it is. I don't need to worry about rewriting it in some other way. Pi over 3 is the solution to the inverse sine of square root of 3 over 2. Lastly, inverse sine of 2. So what I'm asking here, and I'm going to say it probably thousands of times after this, what angle has a sine value of 2? I want to pause there for a second so that you can really think about that. What angle has a sine value of 2? And I certainly hope that all of you can come up with none. Remember that the sine function, as it rotates around the unit circle, goes from 0 all the way up to 1, down to 0 again, down to negative 1, and then back to 0 again. It will never reach 2. In fact, it will never even reach 1.00000001. It never gets any higher than 1. So this does not exist. There is no angle with a sine value of 2. Now let's start looking at what the graph of the arcsine, or the inverse sine, looks like. It's actually quite simple. We looked at how we restricted the domain before. So it's simply a matter of taking values in our restricted domain, which again we restrict it between negative pi over 2 all the way to pi over 2. Essentially what I'm doing here, I could think of these as my x values, and I could think of this as the sine of x. Okay, and I could just plug in what is the sine of negative pi over 2? Negative 1. What is the sine of negative pi over 4? Negative square root of 2 over 2. What is the sine of 0? That is going to be 0. What is the sine of pi over 4? That is going to be the positive square root of 2 over 2. And what is the sine of pi over 2? That is going to be 1. Now, once I've thought of it that way, if I want the inverse, hopefully we can all remember that an inverse simply just switches the x values with the y values. Right? So now what I'm looking at is instead, oops, that should just be x, is instead having my x values be what were originally before the sine values, and my outputs are now the inverse and the angle values. Okay? So once I've swapped the two things, I can graph them on a coordinate plane. So this is what the inverse sine function looks like. The inverse cosine function is going to look a lot like this as well, but it's going to be restricted on a different domain. But it's going kind of vertically instead of horizontally. It's not going to move past -1 in this direction, and it's not going to move past 1 in this direction. That does not exist. Cosine. Like I told you, it's going to be very much the same as the sine function, except that it's restricted on a different domain because the shape is slightly different. The sine function was restricted from -π/2 to π/2. If I had done that here, again, horizontal line test, boom, not going to work. For the cosine function, the place where none of the values intersect or overlap is between 0 and pi. All right, so the restriction of the domain for cosine is between 0 and pi.
Are now just broken.
That's what this
There's like a hammer and
How's it going?
broken.
How's class?
Right, again, we have different ways of writing it: arc
Cool.
cosine and inverse cosine function, meaning the exact same thing. Not really a big deal. The same thing is true for the tangent function. The tangent function's restriction is very much like the sine function's restriction, because the tangent function goes and does things like this over and over and over. One of these little squiggles, if I restrict it from here to here, one of those little squiggles does not show any sort of repetition. So one squiggle is a good restriction of the domain, and we just choose the -π/2 to π/2 restriction because it's the simplest. So let's try and use this inverse idea and the restrictions in their domains to solve for other kinds, the cosines and the tangents. Alrighty, so we are looking first at arc cosine of the square root of 2 over 2. Well, basically what we're asking ourselves here is what angle value gives us a cosine of square root of 2 over 2. So if I look at a unit circle, I can see square root of 2 over 2 comes up in areas that involve pi over 4. It's pi over 4 and 3 pi over 4 and 5 pi over 4. But when it's positive, it's going to be in, boom, this one or this one. So I'm looking at either the pi over 4 angle in this or this one. Now when I think about the restriction of the domain of the cosine, of the inverse cosine function, that's from 0 to pi, which means this. Which means I don't care about that one. This is the only one that I care about, which is pi over 4. So the arc cosine of the square root of 2 over 2 is pi over 4, not this one down here. Now let's look at the inverse cosine of -1. Does it matter that I'm using inverse cosine? No, it does not. Boom! Look at that. I have extra room. So I'm doing the inverse cosine. Forgot. -1. Fantastic. So what angle gives me a cosine value of -1? If I look at a unit circle, I know that the cosine is -1 right here, and that angle happens to be pi. Is pi between the restriction of 0 to pi? Yes, it is in that restriction. So my solution is pi. That was an easy one. I feel like that was too easy. Let's look at some tangent stuff. Arctan of 0, I believe, was that one, and arctangent -1. Let's just double check that. Yep. Cool. So arctangent of 0. What angle gives me a tangent value of 0? Huh. Interesting. When does tangent equal 0 is an interesting question just in general, because it's basically a fraction, right? It's sine over cosine. So what happens if I have, oh, I don't know. Let's do 0 over 1. If I have the sine equals 0 over 1, what exactly does that do to this entire thing? Well, it equals 0. What about if I have cosine over, oops, not what I meant. What happens if I do that sine over cosine equals 1 over 0? I have division by 0, which is undefined. Those are the places where the tangent function is undefined. So what I'm looking for is a place where sine is 0, and that happens to make the cosine 1. Well, that's at 0 degrees, 0 radians, that's a 0. Now I need to think about, is 0 within the restriction of the tangent, the arctangent function? I look at a unit circle, boom, boom. The tangent function is restricted from here to here, right? Just like the sine function is, from negative pi over 2 up to pi over 2. And 0 happens to be right dab in the middle of that. So my solution is 0. Now I need a place for the arctangent of negative 1. So an angle value that gives me a tangent value of negative 1. Again, tangent is sine over cosine. How is it possible that sine over cosine could equal 1? Well, the only place that could happen is if sine and cosine are equal to each other, right? Because then it'll be something over itself. So where are sine and cosine both the same value? Well, if I look at a unicircle again, I have these places. Boom, 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 boom. All kind of variants of pi over 4. Over here it's 3 pi over 4. Over here it's 5 pi over 4. Down here it's 7 pi over 4. Now I need to ask myself, which of these values are within the tangent function? Well, the tangent is restricted again between negative pi over 2 and pi over 2. So it's over here, which means I don't care about any of these. And then 7 pi over 4 technically is a rotation that goes all the way around and to here. So I don't care about 7 pi over 4 either. So what else can I do? I know also that this one up here is going to end up getting me square root of 2 over 2 over square root of 2 over 2, which is going to get me a positive 1. So I really don't care about this one either. I exhausted all of my options. So that's not very good. This one down here really wasn't a bad option. It wasn't quite written correctly. If you remember a couple examples back, all I had to do was change the way that this was written, and it somehow worked. So I'm going to change this to negative pi over 4, because that's another way of writing this just as a negative angle instead of going all the way around and getting there. So with it being negative pi over 4, does it work? Well, the sine will be negative square root of 2 over 2, and the cosine will be square root of 2 over 2, which equals negative 1. That is an angle whose tangent value is negative 1. So my solution for the arctangent of negative 1 is negative pi over 4. Alrighty, that was a bit of a long one. Let's all take a breath. Let it relax, because we're going to go into compositions of functions, something that probably wasn't your favorite thing to do in Algebra 1 or Algebra 2, but here it actually becomes pretty easy. We need to remember what a composition is and how exactly that works out with inverses. A composition is when you take one function of another function. So here I have the function value of f inverse of x, as well as f inverse of f of x. Now, what happens when you take the composition of an inverse in the way that we have it right here in these two examples? Well, if I take the function value of the inverse of the variable, what I'm left with should be the variable if these two things are inverses of each other. And if I take the inverse of the original function of the variable, again, I should get the variable if these two things are inverses of each other. So these things are very, very true in the terms of the inverse sine, inverse cosine, and inverse tangent functions to an extent. There's always a little bit of an issue because we kind of cheated and restricted that domain. So things aren't as black and white, straightforward as you might hope. If you're the type of person who prefers to just memorize properties, then this would be very important to you. For me, I personally just like to go for it and kind of internalize the ideas of their domain and range and then work through it that way. And I'll show you what I mean here in this example. If I have the arcsine of the sine of 3 pi over 2, I have the inverse function of the original function of this. So if that's true, my solution, like if inverse properties are true, my solution should be 3 pi over 2. Right? I should just be able to go boom, boom. Those two things are inverses. My solution is right there. But in this case, if I actually were to work it out from the inside out, if I do the sine of 3 pi over 2, that gets me negative 1. And if I do the arcsine of negative 1, it's actually negative pi over 2, because 3 pi over 2 isn't within the restriction of the domain. Okay, so my solution isn't actually that simple, but all I really had to do was think Okay, I know 3 pi over 2 isn't within the domain. What's the other way of writing that with a negative angle? Okay, it's negative pi over 2. That's my solution. All right, that is an example of one of the properties that's written there. So again, if you're somebody who likes to memorize the properties, that might be easier for you. Let's look at some others. For part A, I have the tangent of the arctangent of negative 5. But technically, that's good. I should be able to just go boom, boom, and say that my solution is negative 5. But, does that particularly work? Does negative 5 lie within the domain of the arctangent function? Now let's remember tangent. Tangent originally does something like that. Now its inverse function is basically going to be flipped, which means now its inverse function doesn't go from negative pi over 2 to pi over 2, but it does go on forever to the right and left along the real axis. So negative 5 actually is within the domain, and I can just cross them out and say that my solution is negative 5. Okay, you might have to keep referencing back to what the domains and ranges of these inverse functions are, and that's fine. It is going to take a little bit to get used to. Now for part B, I have the arcsine of the sine 5 pi over 3. Now, what do I have to do here? Essentially, I have the inverse function of the function, so I should be able to go boom, boom, and then this is my solution. However, is 5 pi over 3 within the restricted domain of negative pi over 2 to pi over 2? Unfortunately, it is not. So, what I need to do is find an angle that's coterminal with 5 pi over 3 that's within that restriction. So what I'm going to do is 5 pi over 3 minus 2 pi, and that's going to give me that new angle that's coterminal. So I need a common denominator of 3, that's going to make that 6, that makes that negative 1 pi over 3. That is my solution. I can cross these things out, but I need to change this angle to a coterminal angle that's within the restriction. And lastly, the inverse cosine of pi. All right, let's check it out. Inverse cosine of pi. That's basically me asking what angle has a cosine value of pi. Cosine value of pi. Pi is, let's just say, it's around 3.14. It's not exact, but so what angle has a cosine value of 3.14? This is kind of trying to trick you in a way by putting it as what you would assume to be a radian value. But we need to remember that when I'm looking at the inverse of a function, this should just be a number between negative 1 and 1, right? If it's not a number between negative 1 and 1, I can't do the inverse of it because it doesn't exist. Cosine only goes as high as 1 and only goes as low as negative 1. There is no angle that could possibly give me a cosine value of 3.14. So this does not exist. Not applicable. DNE does not exist.
All this math is making
Alrighty.
my head kill.
I had extra room! But good news for everybody, that is the end. So, try out the exercises that are assigned. I know that this is going to be a little bit weird, trying to get used to all the new domain and range type stuff. There's a lot of things to wrap your head around. This is the last section of this chapter. I will see you guys in class. We can go over whatever we need to. Good luck. Enjoy it. Live life to the fullest.